Okay, well, thank you for coming this afternoon, especially on the nicest day of the year. It's very nice that people actually came inside. So crossing the blood-brain barrier one bite at a time. That's not a particularly intuitive title as to what it means. So today, Nick and myself are going to be talking about some of the methods that we use at Lawrence Livermore to try and optimize drugs to get into the brain so they can be more effective. And as you'll find out during the talk, that's not particularly straightforward. So first things first, a little bit about myself. So my dad was a chemistry teacher, so growing up, he instilled this sense of appreciation for science in me. So I'm hoping that I can do a little bit of that with you today. And secondly, I work at a US government national lab in Livermore, California. I live in Livermore, California. As you may have noticed, I am not American. I am British. So what? How am I here? So it turns out I was on vacation and I met this girl from Modesto, and that was 11 years ago, and now here we are. But that also means, being British, I say a lot of strange words with a strange accent, apparently, like boot, torch, and petrol, and also computational biophysicist, which is me. So hopefully by the end of the talk today, you'll have a little better understanding of what a computational biophysicist is and what they do all day. And I'm joined out here with my partner in crime, Nick, so he's going to take over the reins now and tell you about what he does.
Well, thanks, Tim. So I'm Nick. I'll just do a really quick introduction and then we'll get right into some of the science that we're going to talk to you about today. So, as you might be familiar, being a scientist or the process of becoming a scientist involves a bit of training. So, there's some school, there's fellowship, there's other stuff. So, just in case you're not familiar with what that looks like, I thought I'd bring along a picture of myself while I was doing my training, where I worked relentlessly, night after night, doing nothing but studying and working in the laboratory. And so, ultimately, just in case my dream of being a rock star didn't quite come through, I decided to take the much more glamorous job of being a scientist, and that's going to be a little bit more of what I talk to you about today. So, as you might imagine, there can be many different illnesses, many different diseases that you might want a drug to treat. And one of the things that you want to consider if you're trying to treat an illness, trying to treat a particular disease, is getting the drug to where it needs to be. So, one of the ways you can do that is take a drug orally by mouth, goes down to your stomach, and then hopefully goes throughout your circulatory system and gets to the place where it needs to be. So if you're trying to treat a disease in the kidneys, you would want to get something to the kidneys or into the liver or anywhere else in the body where you might have a particular illness that you would want to handle. What we're going to talk about today is the brain. And as you can see up top, the brain is indeed special. Your brain is special. And one of the reasons that it's special is that it doesn't regenerate or recover as quickly as other organs in your body. And because of that, you need to have specialized mechanisms that protect your brain. That's one of the things we're going to tell you about today, is something called the blood-brain barrier. Now, the blood-brain barrier is a structure that prevents things from the blood that you don't want into the brain from actually passing into the brain. And the reason that this is important is that there's actually a ton of blood in your brain. What we're seeing here is the network, the structure of blood vessels that run all through your brain. And this picture this is an actual representation of what those blood vessels look like. And the way that they build this is to inject a liquid resin into the brain, and then it hardens, and when you remove the tissue, you can actually see those vessels from the larger ones at the base out to the very, very small ones on the very edge. And so because you want your brain to be protected, because it doesn't recover quite as quickly as other organs in your body, you need a barrier around those blood vessels that keeps harmful things that might be in the blood from passing into the brain tissue. So what exactly does this look like? This is a cartoon representation of just what an average blood vessel in an average tissue might look like. So up top, you have red blood cells that are running through your bloodstream, you have some cells, and then on the other side you have a tissue. Maybe it's the kidney, maybe it's the liver, any tissue that you might want to get a drug to. And here you have a therapeutic drug floating around in yellow through your bloodstream. So in an average tissue, you might be able to get in between those cells. So there are spaces in between those cells that a drug can get in between and get to where it needs to be. The brain, however, is special, like we've been saying. So instead of these spaces in between the cells, they're packed with specialized proteins. We call these tight junctions. And what these do are just kind of what you would expect. They block the spaces in between those cells. So if you get a drug, it just kind of bounces off of all of those proteins, of all of that structure that's packing into that space, and it protects whatever tissue is on the other side, in this case, the brain. So if we have something that we want to treat in the brain, what are we to do? Because it's going to be very difficult for us to get a drug into the brain using a conventional approach. Another way that you can get something through cells into a tissue, in this case into the brain, is to go right through them. So we're going through the top, across the middle, through the bottom, and then finally into the brain tissue. Now, you might be familiar from a biology class, the fact that surrounding cells are something called a cell membrane or a plasma membrane. So if we want to design a drug that's capable of getting into the brain by actually passing through the cells and getting through the cells to the brain, we need to understand those membranes. We need to understand their structure. We need to understand how they interact with things around them. And so to help explain a little bit more about how we do that, Tim is going to talk in some more detail about those membranes.
Thank you, Nick. So like Nick said, in the brain, these drugs have to go through the cells. In order to do that, they have to cross the membrane, go through the cell, across the membrane again. And you can imagine that most of the inside of a cell is water. Most of the outside of the cell is also water. So these membranes effectively have to act as a barrier to water. And they do this by building upon two chemical properties as to whether a compound is hydrophobic or hydrophilic. And hydrophobic means that those compounds really hate water. They don't like interacting with water. Whereas a hydrophilic compound is the opposite. They really do like interacting with water. But also, importantly, is that hydrophobic compounds like to hang out with each other, and hydrophilic compounds like to hang out with each other. But they really, really hate interacting. Much like Cal fans and Stanford fans, for instance. And so this property is so important that if you have a bunch of them all mixed together in an environment, all of these molecules are going to be really stressed because they all have to interact with a different type of molecule that they don't like. So if you leave them long enough on their own, they will reorganize so that you have all of the hydrophilic molecules on one side, all of the hydrophobic molecules on the other, and now they're a lot happier because they don't have to interact with the people that they don't, the things that they don't like. So how does this property pertain to cell membranes? So on your left-hand side of the screen, we have a water molecule. As some of you may be aware, this water is H2O, meaning there's one oxygen atom, two hydrogen atoms. So the oxygen is shown here in red, and the two hydrogens in white. On the other side, now that's a strange-looking molecule. That is a lipid, and a lipid is the component that makes up cell membranes. And what makes lipids really interesting is that they are not just hydrophobic or hydrophilic, but you have one end called the head, which is hydrophilic. It really likes interacting with water. And at the other end, you have these two tails, which are both hydrophobic. So this means it has these strange properties where it likes water and it dislikes water at the same time. So if you just have a single lipid molecule and you put it in water, there are water molecules surrounding it. Because most of the lipid molecule, the tails, are hydrophobic, it means that a lot of the water molecules are going to be unhappy with that situation. The waters don't want to interact with the tails, and the tails don't want to interact with the waters. So what happens in the cell membrane, if you have hundreds and hundreds and thousands and millions of lipid molecules in water, they start to form different structures to minimize the interactions between the water and the tails. And to illustrate that, we have a short movie where you can see you have a water molecule, a lipid molecule that's in water, and then if you have two of them come together, they will pack together, the tails will pack, so that now there are less water molecules to interact with those tails. And if you extend this process again and again, you find that they form these really cool structures called lipid bilayers. So you have one layer of lipids on the top, one layer of lipids on the bottom. Suddenly, none of the tails are interacting with water. Only the hydrophilic head groups are interacting with water. And it's this structure here, a lipid bilayer, which is a cell membrane. So now you have water which is outside of the cell, water inside of the cell, and you have this hydrophobic cell membrane that separates the two. And this is exactly what a cell membrane is made up of. You have this hydrophobic barrier that keeps hydrophilic things outside and also other hydrophilic things inside. So the point of this talk is how we optimize the effectiveness of drugs. And effectiveness of drugs comes down to two components. Their activity, how well the drug actually does its job, and also accessibility, how well it actually gets to where it needs to be to do its job. Now this becomes an issue when we think about the cell membrane, because a lot of drugs and a lot of drug targets are hydrophilic. So if you have a hydrophilic drug that's on the inside of the cell, or on one side of the cell membrane, the blood-brain barrier, sorry, and then you have your hydrophilic drug that's on the other side of the membrane, this hydrophilic drug isn't going to want to cross the hydrophobic cell membrane, because those properties don't really like interacting. So in order to try and solve this problem, what we can do is we can modify the drug slightly. We can take the hydrophilic drug in red and add on a small component to it that is hydrophobic. So now your drug has both properties, it's able to cross the membrane, and it gets to its target. But unfortunately, it's not, as with most things in science, it's never quite that simple. Because if you make this hydrophobic part too large, now here the blue part is a lot bigger than the red, now suddenly the drug is more hydrophobic. So if it gets into the cell membrane, it actually turns out it prefers being in there, and it doesn't ever leave again. It doesn't get out to the other side. And the other problem is that if you make the hydrophobic part slightly the wrong shape, or have some other weird features, it means that it may cross the membrane, but when it gets to the target on the other side, it no longer does its job properly. So now you have accessibility, but that's at the cost of activity. So to put this into some other terms, it's like if you had a chore, and your chore was to mow the lawn. And you're like, okay, I'll mow the lawn, I'll go out and I'll use the most up-to-date, high-tech, all singing, all dancing lawnmower that I can find. It will do the job, and I won't have to do any work. It will practically do it for me. But the problem is the lawn that you have to mow is behind a picket fence that has a narrow gate. Now you have the best tool in the world, but you can't lift it over the fence. It weighs 2 tons. You can't get it through the gate. It's far too narrow. You have the best tool in the world, but it's useless for the job that you need it to do. So a compromise would be to have a lawnmower that's perhaps not quite as good, but it's a lot lighter, it's a lot smaller. You know, you can take it over the fence, you can go through the gate. It will get the job done. But then if you take this to the extreme, you could have something that's really, really accessible and really easily get across the fence, but I wouldn't, I mean, technically, you could use it to mow the lawn, but I wouldn't want to do that. So these are some of the features that we have to weigh up when we talk about our drug optimization pipeline. So in order to try and find the right optimizations, the right hydrophobic pieces to add to our drug, it's critically important that we are able to predict the drug's permeability. How will the changes that we make to the drug influence its permeability across the membrane? And to talk more about that, I'm going to now pass it back on to Nick.
Thanks, Tim. So Tim's talked to you a little bit about all of the different parameters that we need to understand about a drug. How effective is it? How permeable is it? Is it actually going to get to where we need it to be? And so there are different tools that we need to use in order to assess all of those unique factors. So we need to understand all of those factors so that we can compare different drug candidates and see which ones are going to work better, which ones are going to be going to the places where we actually need them. And so I'm going to talk about 3 different tools, or 3 different classes of tools here, introduce them, and then we'll talk about them in a little bit more detail. So one tool that we can use are in silico tools. These are computational tools for understanding how permeable something is. How quickly or capably is something going to get across a membrane? And here, we're building models, we're building simulations of membranes to try and predict how well various drugs are going to go across. We also have what we call in vitro assays, or in vitro cellular assays. And this is where we're taking those simulations that are done in the computational system and taking them actually into physical reality and testing them in the laboratory, testing them in experimental systems. So these might be artificial membranes that we're actually testing candidate drug compounds against. And so the last tool we have are in vivo, or animal models. And this is where you have a complete biological system. So you have all of the different components that you might need to understand, and you can see how they interact with each other, ranging from the bloodstream to the brain to all of the molecules in between. Now, like with any set of tools, these have various advantages and disadvantages. So we'll go through those really quickly to try and understand why we might use one of these tools in one case and another set of tools in another. So one of the things you would want to understand when you're evaluating any set of tools or any set of work that you're trying to do is how accurate is the measurement that you're taking. If we're looking at the computational system, this tends to be a little bit less accurate because you don't have all of the complete systems modeled in that simulation. You might just have the membrane without other proteins that sit in the membrane, or you might just have different components or smaller pieces of that membrane. On the in vitro side, it's going to be a little bit more accurate because you have a complete system of membranes, for example, an artificial set of membranes, or maybe you have a set of cells, but still you don't have the complete biological system. You don't have the circulatory system and the gastrointestinal system, the brain and everything else together, and that's why the animal model is actually going to be the most accurate system. Now the other thing we want to think about is cost. So while the computational system is maybe not quite as accurate, it is much more cost effective because we don't actually have to build any of the drug molecules that we're testing. We can just create them, simulate them on the computer. We have to actually build those compounds to test them in our in vitro, in our experimental laboratory models. And so those tend to be a little bit more expensive, and the most expensive model is going to be the animal model because of all of the infrastructure and the large team that is involved in bringing that together. Now, the last thing we want to think about is time, because of course we want to think about how long is something going to take. So the best one for time is, again, going to be that computational model because we don't have to build the compounds and we can immediately create them on the computer and immediately test them. It's going to take a little bit more time to do the in vitro assay because, again, you have to build those compounds, you have to have your artificial experimental system to test against, and then the most time is going to be the animal model because you have a lot of animals, you have a lot of infrastructure and a lot of teaming and a lot of individuals who have to come in and be part of that experiment to make it successful. So because of those various pros and cons, we can approach the design of a drug and the evaluation of a drug in a specific way, where we start with hundreds of compounds. Say we have hundreds of candidate drugs that we want to try and test just to see how well do we think they're going to work. Because we can do things quickly and cheaply in the computational model, we can test hundreds of things at a time. We can then make predictions about which of those we think is going to be most successful, and we can, select maybe just tens of compounds to test in the experimental system. And so we can do a smaller number of compounds in a system that's a little bit easier, a little bit faster, doesn't cost quite as much. And then we can just select maybe the best one or two of those that are going to work in our most expensive, most time and cost-intensive model, the animal model. So this shows kind of a process where we start with many things that we think might work, and then we try to intelligently reduce the number of things that we're testing so that we can be as efficient as possible. So we're going to talk now about some of the specific ways that we're applying these tools, and we'll start with the computational side. So one of the questions you might have is, what exactly is computational biology, and what does a computational biologist do all day?
Thanks, Nick. That is a great question. And there are several people in the audience who have asked me that. What does a computational biologist do all day? It does seem a bit contradictory that you'll have someone who does computational work but in relation to biology. Those two things don't really seem like they are connected. So I found this cartoon online, which I think is quite, sums up my life sometimes. You see that the computational biologist doesn't really have to deal with the restrictions that the experimental biologist has. My lab is just an office. I just sit at a laptop. I can wear what I want. I can have drinks. I can have food. There's no restrictions. Hypothetical experimental biologists, on the other hand, they have to work in the lab, there's lots of restrictions, they have to wear protective gear, they can't take any drinks, sometimes the chemicals that they're working with can be quite dangerous, or things like that. But of course, reality is much, much different. I mean, I often wear a hat.
Also, experimental biologists tend to be charming. The computational biologists are very good at drinking coffee.
But yeah, also, you can see the experimental biologists are generally kind of moody that they're rock Korean. So, what does a computational biologist do? What is computational or in silico biology? And from my point of view, when I talk about computational biology, I really mean molecular dynamics simulations. No one's heard of this before? No? Okay. Yes, molecular dynamics simulations, the way I would describe this is saying that I do animations of biological systems at the scale of an atom, where these animations, the movement of the atoms, are driven by physics. So I'm going to go into this in a little bit more detail and try and break down these two bullets. First of all, animations. I'm going to define, for the sake of this talk, animation as the movement of something over time. Now you think of an animation, you have a static image. You can move pieces of this static image a little bit, and you get another static image. You can then take that new image, do the same thing again, move it a little bit, get a new image. You do this over and over again. You recreate movement. Does anyone recognize this horse? Anyone? So this is actually thought to be the very, very first motion picture ever in the world that was the result of, I believe, a bet, change in position over change in time, result of a bet between Leland Stanford and his prestigious university, and whether or not all four legs of a horse left the ground when it was at full gallop. And this was in 1878, so there wasn't any iPhones back then. You know, and no one really knew the answer to this. And the way they resolved this was by setting up lots of cameras along the race course that was each had a tripwire attached to it. So when the horse ran by, each camera took a static image. And because the cameras were arranged sequentially as the horse ran along, those static images were related in time. So it effectively became the world's first motion picture, the world's first animation. So animations, a change in position over a change in time. And this animation, the one of the horse, what is driving the change in position here is the actual physical movement, motion of the horse. But in other types of animation, what is driving the change in position is the imagination of the animator. They can make the animation do anything they want. It's only limited by their imagination. That's what's driving the movement. In my animations, when I animate things, what's driving the change is physics. I'm not telling it what to do. Physics is telling these different atoms and molecules how to move. And so animations which are driven by physics. And the physics that I use is not new physics, this is Newtonian physics. So Isaac Newton, who probably most of you know for discovering gravity, when an apple fell on his head. So Isaac Newton, like all great, brilliant, handsome scientists, he was British. And so he also had, as well as discovering gravity, he had these laws of motion. And his second law of motion states that the acceleration of an object is equal to the force imposed on that object divided by the mass of the object. So that essentially means the harder you kick a soccer ball, the faster it's going to go. But also, if you want to kick a bowling ball, it's going to need a lot more force imposed on it. So we can rearrange this equation, say that this is how you calculate acceleration. But the definition of acceleration is something's change in velocity over a change in time. And in turn, the definition of velocity is an object's change in position over change in time, which is how I'm defining animation. So in order to animate something, to get it to change in position over change in time, I just need to calculate the acceleration. And this equation tells me how to do that. We already know the mass of all the atoms in the system. I just need to find the force on the atoms in order to animate the system. So that's what I spend most of my time doing, calculating the forces on these atoms. So I'm going to go through an example now of what I mean by the forces on the atoms and how this actually works. So we're going to start off talking about a very simple molecule that I talked about earlier, water. That's quite timely. So water, as I mentioned earlier, is H2O. Does anyone know what this is? So yeah, my dad was a chemistry teacher, so I had these like lying around the house when I was growing up. They're kind of like Lego sets for chemistry molecules. You can use this to build any chemistry molecule in the world, including two of the most important molecules known to man, caffeine and sugar. But we're going to build water. So water, H2O, has one red oxygen atom, so we'll take one oxygen atom, and we're going to bond two hydrogen atoms on that. So we're going to take two hydrogens and two bonds, let's take those. There we have one water molecule, H2O. We'll make our system a little bit bigger. We'll have three water molecules in there. We have three water molecules, 9 atoms. I'm going to start by explaining how I calculate the forces on just one of these atoms. Let's say this hydrogen atom. And to work out the animation, the movement of this hydrogen atom, I need to know the net force. And by the net force, I mean that you can have two forces acting on this, but it's only going to move in one direction. It's like if you have a tug of war on this hydrogen atom, and the team on one side has more people, the force is bigger in that direction, so the atom's going to end up moving in that direction slightly. So the forces that are calculated on these atoms fall into two different categories. We have the bonded forces, which mean forces between atoms that are in the same molecule, and then we have the non-bonded forces. And this is how atoms in different molecules interact with each other. So I'll start by talking about the bonded forces. Come back to our water molecule here, and the bonds are shown as these little kind of white lines connecting the atoms. But bonds, and the way we treat them, are kind of like springs, meaning that there's some movement allowed there. And much like springs, these bonds can expand and contract. But also like springs, as you pull them further apart, a spring acts to kind of pull everything back together. And likewise, if you compress it, the spring will try and come back to its normal length. And bonds behave kind of the same way. Every single bond between different types of atoms has an ideal length that it wants to be at, that it's happiest at. If you stretch that bond, it's going to try and pull back. If you compress it, it's going to try and expand again. So we know what the ideal bond length is between an oxygen and a hydrogen. And we're going to pretend that in this system, that the bond length has been slightly stretched for whatever reason. Meaning that there's going to be a very small force on that hydrogen, pulling it back so that the bond length returns to its ideal value. The other type of bonded force is the angles between different atoms. So for instance, between the hydrogen, oxygen, and hydrogen, there's an ideal bond angle. The angle at which all those atoms are happiest and everything is most relaxed and calm. And again, much like the bond length, if you start to disrupt that, if you compress the angle, the atoms are going to try and move back to their relaxed angle, and if you overstretch them, they're going to contract again. So in this system, we're going to pretend that the angle is slightly compressed, meaning that there's going to be a force on our hydrogen to try and bring it back to this natural relaxed angle. Everything in physics tries to get to the most relaxed, kind of non-stressed state. So these are the two types of bonded forces we deal with. Moving on to the non-bonded forces. Now all atoms have kind of like a very small like gravitational pull. They kind of just attract each other a little bit. So everything that's within a certain distance of our hydrogen, that's illustrated here by this dotted line, is going to have a slight attractive force on our hydrogen atom. So that means it's these ones here that are kind of highlighted in blue. So all of those will exert a small force, a small gravitational pull on our hydrogen atom, as shown here. And the result of these three forces will look something like this. There'll be a force in this direction because of the atoms that are close by to our hydrogen. And the final type of force is electrostatics. All of these atoms have either like a slight negative or a slight positive charge. And again, the atoms that are close enough within the dotted arc there will have an effect on our positively charged hydrogen atom. So we have that big negatively charged oxygen, and because they're opposite charges, they're going to attract each other. There'll be a big attractive force from the negatively charged oxygen on the hydrogen. But there's also these other two positively charged hydrogens, and like equal charges will repel each other. So there'll be forces from those hydrogens that'll push our hydrogen away in the opposite direction. So all of these three forces will result in something that looks like this. And that's the last step for the force calculation. So we have the four different types, two bonded, two non-bonded. Now all we need to do is add them up. Bonded, non-bonded plus bonded, we have the four different forces, different magnitudes, different directions. We end up with a net force on this hydrogen that looks like that. So now we have a force on that hydrogen with a direction. We can calculate its acceleration, we can calculate its movement. So we just do all of that again for every other atom in the system. So now we can calculate the acceleration and generate the next frame in the animation. Hey! Everything has moved a very, very, very small amount. And because they have moved a very, very, very small amount, now all of the forces on them have changed slightly. So we have to calculate all of those forces for all of the atoms again, and again, and again, and again. And just like with the horse, you have these frames, you put them on top of each other, you have something that resembles movement and motion. Except now the way that these atoms and these molecules are moving is driven purely by the way, the physics and the chemistry of how they interact with each other. So this is an example, a system with 9 atoms, 3 molecules, and for about 10 frames. So the types of simulations that I do to help try and predict the permeability of a drug are a lot larger than this. So in these systems, we have a membrane, just like we do in biology. We put water on either side of that membrane, and we put our drug molecule somewhere in the system. So this system, instead of having 9 atoms, has closer to about 25,000 atoms. To calculate the net force of every one of those atoms takes about 100 million calculations. And in order to run this simulation for long enough to get good statistics and a better sense of confidence in our answer, we need 50 million frames. So that means the total number of calculations for one of these systems is 5 quadrillion. That's 5 followed by 15 zeros. That is a big number. I didn't know what it was, I had to Google it. And this is why we need supercomputers to do this. Okay, so we've run our 5 quadrillion calculations on our system. This is our cartoon system. Now I'm going to show you what that actually looks like. This is an example system where I've represented all of the atoms by little beads. You have water on either side, you have a cell membrane in the middle, and the hydrophobic tails are in yellow. Now this can get really confusing and kind of give you a migraine if you look at it for too long because all the atoms are kind of moving around. So I'm going to put it in a representation that is easier to follow what's going on. But it's important to remember that these kind of squiggly spaghetti things, there's actual atoms under there that define their positions. So 2 things now for this movie. The positions of all of these things there's really atoms there. And secondly, I haven't told this what to do. I didn't sit there and move it a little bit, take a frame, move it a little bit more. I set the system up, started the calculations, and it was physics that defined how this moved. So there are 2 things I want you to try and look at. I want you to look at the behavior of some of the water molecules as they interact with the membrane. And I also want you to look at the orientation of this drug molecule. So this drug molecule is going to end up being colored two different ways. One end will be red, meaning that it's hydrophilic, likes to interact with water. The other end will be blue, meaning it's hydrophobic, doesn't like interacting with water, but likes to interact with the lipid tails. So we run the simulation. You can see some of the water molecules, they try and go into the membrane and then realize, oh, no, we don't like this, I'm going to go the other way. And also the orientation of the drug molecule at the top, it will reorient itself so that the hydrophobic end that doesn't like water is always facing into the membrane. And again, this is purely the physics of how these molecules interact with each other that defines how they move. So these are the types of simulations I run. So the question now is, how do I get the predicted permeability of that drug from doing these simulations? Well, in an ideal world, we'd just start the drug on one side and start a stopwatch and see how long it takes to get to the other side. But unfortunately, even with the unbelievable computing power we have at Lawrence Livermore, this would still just take too long. We wouldn't get reliable answers, and we certainly wouldn't be able to do it in a high throughput way to test hundreds of different compounds. So we have to come up with a method to get the answer quicker, faster, cheaper, smarter. So the analogy I have is, this is a fairly steep hill near Livermore called Patterson Pass, and it's very popular with cyclists to try and get to the top. So this scenario is, if you wanted to know how much energy it would take to get to the top of Patterson Pass on your bike. So the simplest, most straightforward way would be to get your bike, get a cycling computer, put it onto the bike, and cycle to the top, and then see what the computer says. But unfortunately, you know, it kind of gets hot, and you had a lot for lunch, and you're kind of a slightly out of shape scientist, and you never get to the top. You never get your answer, no matter how many times you try. The path is just too long, too steep, you can't get to the top. The solution is to head out with a few of your friends. You all have bikes, you all have cycling computers, and you start at various points along the climb. Now, to get your answer, you don't need to start at the bottom and get all the way to the top. You just need to start from your position and go to where your friend started down the road. Now, you turn around, go back down the hill, you get all your cycling computers, and you add up the numbers. Now you have the energy it takes to get from the bottom all the way to the top, but you've only had to go a fraction of the way. And you get the answer. So this is kind of the same approach we use with these simulations. Instead of having one simulation where the drug starts at one end, and we wait for it to go all the way through to the other end, we set up hundreds and hundreds and hundreds of simulations where the drug molecule is in a slightly different position each time. And now, because we have very powerful computers, currently number 2 in the world, I believe, we can run all of these at the same time, and we can get our answer very quickly. So I would estimate to get the answer for one drug molecule would take maybe a couple of days. So to get 20, 30, 40 drug molecules would take a few months. If you wanted to do that on, for instance, this laptop, it would take you probably the better part of 100 years. So again, that's why we need supercomputing to do these sorts of calculations. So this enables us to take a large number of candidate drugs or potential ways to modify our drug to make it more permeable and narrow it down to what we think might be the best 20, 30, 40 modifications that we can make. But again, as Nick said, these are just predictions. So the next stage is for me to hand over what I think are the best compounds and give them to Nick to actually test.
Thanks, Tim. So Tim's talked to you about the power of using computational models to test hundreds and hundreds of different things that, unless we had supercomputing capabilities, we would never be able to evaluate. And then taking those predictions and using them to reduce the number of things that we actually have to study in the lab. So what does that look like when we take these compounds and then actually test them in an experimental system? So what we do as a first step, is to try to just look at these in an artificial membrane that we've created in the laboratory. And these sit inside of little wells and little containers, and they sit in plates that are about this big, and each of these plates are going to have 96 of these individual little compartments that contain an artificial membrane that we're going to test. And just so that we can actually see what's happening inside of here, because we're at Lawrence Livermore and we have tremendous laser capabilities, we'll just open that up like that. And so I think that used most of our project budget to actually get that graphic in the slide. But it allows us to see that inside here we have a membrane that we artificially create in the laboratory. And then we have different compartments on the top and the bottom that represent the outside and the inside of the cell. And what we do from here is relatively straightforward. We take a drug that we want to test, we put it on the top, the outside of the cell, or what would represent the blood side of the blood-brain barrier, and then see how quickly it goes across the membrane and gets inside the cell. And so what we can do from here is to calculate the actual expected experimental permeability, how fast does something, a candidate drug in this case, actually get across the membrane. And then we can compare different compounds to see which ones are faster, which ones work better, which ones are more likely to get to the place we need them to be in order to act, in our case the brain. So one of the things that's really important when we're doing computational simulations and then comparing them to experimental results is to actually assess how well do those results really line up. So that's what we did. We took 9 different compounds, we tested them in the computational system, and then we took those same 9 compounds, and we tested them in the experimental system. And just so there's no confusion, I put a picture of myself over here, a picture of Tim over here on the left-hand side, so we can make sure we keep track of everything. He looks good in blue. So there are 4 different categories that we assign for our candidate compounds. Up top in green, things that are very permeable. On the bottom in red, things that are not permeable at all. And then kind of yellow and orange in the middle. And then we tested these 9 compounds and used the predictions on the computational side, as well as the actual measurements on the experimental side, to put these into these different categories. So on the computational predictions, we have 3 that are predicted to be not permeable at all, 4 that are predicted to be very permeable, and then a couple in the middle. And the actual order of these, the 1, 4, 2, 3, does, in this case, mean something. It means that 1 was the most permeable, followed by 4, followed by 2, followed by 3. So we did the same thing with these same compounds, except that this time we tested them in our experimental system, and we find that the results agree very well. So the same 4 compounds that we predicted were very permeable are actually the same 4 compounds that experimentally were validated, were identified as being the most permeable ones. And the same 3 were predicted to be impermeable, and then the same 2 in the middle. You can see that the only difference here is that the order was slightly different up top, whereas the experimental system predicted 1 to be the most permeable, same as the computational, but then went 2, 3, 4. So the order was a little different, but overall, these results line up very well. And this is really important because if we're making decisions based on the computational predictions on which compounds we're going to not look at any further and which compounds we're going to advance for further study, we want to make sure that we're not throwing out things that might actually have worked really well. So the fact that we see good agreement between our computational and our experimental results gives us confidence that we're not doing that we're not losing things that actually might have worked really well. And so I want to really quickly show what the data actually looks like. So this is a plot of the actual representations from those 9 compounds. On the horizontal, the x-axis here, we have the results from the experimental system. So how fast do these things cross an artificial membrane that we build in the laboratory? On the vertical, on the y-axis, we have the predictions that are made on the computational system. And what you would want to see if these results are more or less agreeing with each other is that those points with each dot representing an individual compound would lie closely along that line. And what we see is that this is actually the case, and we can measure this using what's called a correlation coefficient, or an R-squared value. And what we want is for that to be very close to the value of 1. And we see in this case it's 0.97, which is indeed close to 1. And if we fill in the colors with our impermeable to very permeable, we see that we are again assigning these compounds into the same category, regardless of whether we use a computational approach or an experimental approach. And again, this is really important so that we have confidence in the approach that we're applying. Now, we've talked to you so far about the lipid components of membranes. Well, one of the things that's important to be aware of is that there are other things that sit in membranes. So they're not just lipids. There are different kinds of proteins or other types of carbohydrates or other things that sit in a membrane that can have an impact on how quickly a drug can get across it. And I'm going to focus here on one particular component in that membrane that's really important for understanding and predicting whether or not a drug is going to be able to cross and get to where we need it to be. And that's a pump. So what this pump does is it's another component of the blood-brain barrier. So if you remember back to the beginning, we need to protect the brain, so we have this barrier that keeps things in the blood from getting in if we don't want them to be there. So another mechanism, another kind of second layer of protection that you have are what are called efflux pumps. Now what these do is if a drug does get inside, so it does permeate, or any other molecule that does permeate, but you don't want it to be there, what these pumps can do is they can just pull those back in and then pump them back out. So even if that thing is capable of getting into the brain by crossing the membrane, the pump is capable of getting back out so it doesn't potentially do any harm. Now this is a problem for us if we're trying to do drug design, because if our drug is highly permeable but is pumped right back out, that doesn't help us, because then it's not going to be sitting in the brain for long enough for it to actually be doing what we want it to do, and that is acting on the therapeutic target that treats the illness or disease that we're interested in approaching. So what we want to do is also have a model that not only includes membranes or lipids from those membranes, but also includes proteins and all the other things that a cell has associated with it that might impact drug permeability. And so we take a similar system to what I described before, except that instead of just lipids in that artificial membrane, we have actual cells. And here we're using the actual endothelial cells, the cells that coat the blood vessels that make up the blood-brain barrier. And we create a very similar system. So we have a layer of cells, a monolayer of cells, meaning one layer of cells that compose our artificial blood-brain barrier. Again, we have our two compartments, one that represents the outside of the brain, or inside the blood vessel, and the other that represents inside the brain. And we do the same thing. We see how quickly can a drug actually get across that cell through the membrane, and then does it get pumped right back out? And if it does, then we know that we have an issue. So this kind of gives us a few different layers of information. One, is a drug permeable across a membrane? And second, once it's across that membrane, is it likely to stay there? So that kind of takes us through the central part of this middle tool, the in vitro tool, where we're starting with our computational predictions. We're reducing the number of compounds that are reasonably testable in the laboratory. And then we reduce the number of compounds further to just one or two that we're capable of testing in an animal model. And so what we're going to show you next is a little bit of the result of the data that we get from that final, most accurate, but most expensive and time-consuming model. And so one of the things that I want to emphasize here is that although this is kind of a cartoon representation of the animal data, the quantities here, in terms of the ratios, the number of dots we're showing and what we're going to show them doing, is actually representative of the real quantitative data that we got from this model. So we're going to talk to you about two different compounds here, one in green on the left and one in yellow on the right. Tim's going to start off by talking to you a little bit about the green compound.
Thanks, Nick. So this was the result of an actual project where we applied this optimization pipeline. We started off with this compound in green. That was the one we were given. It showed pretty good activity at doing its job, but it was really poorly permeable. So that meant it wasn't crossing the membrane very well or very quickly. So that means that if you actually put it into a real-life system, it wouldn't work that well. So we ran it through our pipeline and ended up with the orangey-yellow compound on the right that Nick's going to talk about.
So on the right-hand side, on your right, we have a yellow compound that maybe doesn't work quite as well, but when we put it into the animal model, what we find is that actually 20 times as much of it gets into the brain. So going back to Tim's lawnmower example, even though it maybe isn't quite as fast, isn't quite as effective in treating the particular target that we're interested in, so much more of it gets to the place where we need it to be, that is the brain, that overall, all things considered, it's a much better candidate compound, and it actually treats the condition that we're interested in a much more effective way. And you'll see a little bit of this in the movie that we're paired with after this talk, where you have Robin Williams playing the doctor who has a number of patients that have a neurodegenerative condition where they're not able to make a particular chemical in their brain. And they need to be able to get a chemical to the brain that can kind of substitute for that. But they need to find something that actually crosses the blood-brain barrier and actually gets to the place where they need it to be. And that's a really important component of this whole process, this network that we've described to you, where we're trying to design drugs that not only work, but get to the place where they need to be.
Yeah, so this is the drug optimization pipeline, where we have used 3 different types of tools, of methods, to able to scan and test lots of different changes that you can potentially make to a drug to improve how well it works. In our case, particularly improve how well it crosses the blood-brain barrier. And by using this type of approach, where you can do lots of things, test lots of different combinations quickly and cheaply, before only testing 1 or possibly 2 different compounds using the most expensive method, it means that we're able to do this for a lot less money. We can save money doing it this way. And we can also do it a lot faster. So we're saving time, we're saving money, and we're also saving guinea pigs. So that's good. And with that, we'd like to take any questions. Thank you. So that, if everyone couldn't hear that, the question was how do we calculate what the force angles and bonds should be between different atoms? Well, so that is really where I'm standing on the shoulders of giants. That is built upon like 100 years of chemistry and chemistry experiments where people have used real techniques and real methods to calculate these things. Like people do experiments to measure what is the atomic bond length between 2 different types of atoms. And that can vary between, depending on what the atoms are, but also their environment. So the oxygen-hydrogen bond length in water will be different than the oxygen-hydrogen bond length in alcohol, for example. So basically over hundreds of years of physical chemistry experiments, there's basically a big list that's been built up of when you have these atoms in this situation, this is how they behave. And so then we plug that into our model. So
what was interesting in this showing, particularly to me, is you've done the calculations computer-wise.
Can I give this to you?
Oh,
No. Watching the animation. Why the difference between what was successful crossing the barrier that didn't come out through the computer work and the second stage? Because in the animation, in vitro, you had better success. What are the variables that would cause the higher success ratio?
I think we actually showed pretty good agreement between the predictions that we made experimentally and the predictions that I made computationally.
Is the question why were the numbers higher in the experimental model, or
Yes.
why, or faster?
In the vitro.
On the axes?
Yeah.
Yeah.
So part of that I think was because the actual experimental system was as close as we could get to what I had in my simulations, but it wasn't exactly the same. There was, rather than having a lipid bilayer, like I showed in the animations, it was actually 1 lipid layer on the bottom, and then a layer of oil, and then another lipid layer on top. So the molecules actually had to go through the first bilayer, then go through a layer of oil, then the other layer on the bottom. And that was, I think that was done for a number of reasons, to make it a more robust test and a more self-consistent test.
Yeah, but it's a good question, and I think, we try to, that gets to the iteration that has to happen between the computational and the experimental scientists, and trying to reconcile the limitations that each of those pieces have, and get them as close as we can, and at least to a point where, in a relative sense, they agree, even if the absolute number that comes out isn't identical.
It's also useful for identifying, like, we found pretty good agreement, but it would also be, if we found there was certain molecules that there was always big disagreement between us, then we would kind of go back and look, okay, well, is there something in the simulation, in the prediction, that we're not taking into account? Do we need to modify how we're doing it? Or do we need to acknowledge that for this particular type of molecule, there's some feature of the molecule that we're just not getting right in our predictions. So then we will acknowledge that the predictions for the other ones are accurate, but these ones, take it with a pinch of salt, or just do the experiment.
So can I ask that if there are additional questions, you come and ask the scientists, so that those of you who are staying for the movie and want to get your paper stamped can go out to the lobby and get stamped and come back. So there definitely is a little break time here, but we want to make sure that we get to the movie. So if you have additional questions for the scientists, please come up to the apron, and we hope to see you next week. And thank you so much for joining us today. Let's get